Before we begin discussion of our next topic, I just wanted to point out in the previous video, we calculated the percent of an element within a compound. And I just wanted to note that there is the general equation within the worksheet to guide you. In the example, we looked at the fact that there were two carbon atoms. The weight of that, each one was 12.01. The formula weight of our compound was 30.08, and we found the percent of the element carbon was 79.9%. So you can always use this formula here when you're calculating percent of an element. But that brings us to our next topic now, this discussion of this number called Avogadro's number and the mole. So when we talk about a single molecule. So I have one molecule of water, one H2O over here. When I talk in terms of just a single molecule, I say that it would have 18.0 atomic mass unit molecular weight for a single molecule. But in reality, we usually work with at least a larger quantity, maybe not quite a mole. We don't always have to work with 18 grams of water. But this quantity, 1 mole, is given by this conversion factor here, this number that we call Avogadro's number of, we're going to see either molecules, ions, atoms. Whenever we talk about a mole of something, it will always be 6.022 times 10 to the 23rd of whatever we're talking about per 1 mole. So over here, I show that if I have 1 mole of water, I'm going to have 6.022 to the 23rd of those water molecules in this beaker here. And that would weigh exactly 18.0 grams. So notice that there's a direct relationship between the molecular atomic mass unit and the gram as our unit. So where did we get this number from? Well, we have two hydrogens in each, which would be about 2.02, and then each atom of oxygen is about 16. So you can see where they just round it to show us the molar mass in grams per mole is only 18 here. So again, a mole is always that exact amount of matter of 6.022 times 10 to the 23rd, but it can depend on whatever we're talking about when we say there's a mole of atoms, molecules, ions. And this derives from the fact that we assign one atomic mass unit based on pure isotope of carbon-12 weighing exactly 12 grams. So that's where we see the importance of that carbon-12 isotope and defining its mass as exactly 12.000 grams. This number is important to note, Avogadro's number. We're going to use that as a conversion factor when we start doing some calculations. For example, if we want to know how many atoms there are in a certain substance, we can use this molar conversion factor. And that brings us to this terminology here that we call the molar mass. So that is when we have, again, 1 mole of substance, so 6.022 to the 23rd of whatever we have. We're going to say that amount in this unit of blank grams per that 1 mole. So when we refer to an element on the periodic table, we can say that it's either in atomic mass units or it is in grams per mole. So let's take a look at sample exercise 6 here, and let's see if we can calculate the molar mass of glucose. And we're given the molecular formula right here. So let's write down what we have. So we have carbon, hydrogen, oxygen. We have 6, 12, and 6. So I need to multiply and then find the sum. So 12.01, 1.01, and 16 are the masses found from the periodic table. We multiply 6 times 12, 12 times 1, 16 times 6. We add all that together, and the sum we should get about 180.18 grams. And we'll include the full unit of grams per mole here. since we're asked specifically for the molar mass and not just the mass of one molecule. So I mentioned we can use molar mass or Avogadro's number, actually both, we'll see, as conversion factors. So when we have grams as our given unit and we need to get to moles, we would use the molar mass, so what we just calculated, to kind of bridge between grams to moles. So we use molar mass there. And because the unit is in grams per mole, when we use or divide by moles, our molar mass rather here, we end up with our unit in moles. And then say we want to know how many formula units we have in an ionic compound, or how many molecules we have, or even how many ions we have, we can use Avogadro's number. So we would commonly multiply by 6.022 times 10 to the 23rd to go from moles to formula units or whatever other unit we're looking for. So we're going to see many different relationships and many different conversions between moles and grams and formula units using these conversion factors. And just so we can kind of have a summary of everything we looked at, we can see atomic nitrogen here and its formula, and then its corresponding formula weight, how we could write it in atomic mass units or grams per mole and mean the same thing. And if we have just one mole, we have that Avogadro's number, 6.02 times 10 to the 23rd nitrogen atoms. We were talking about N2 here, diatomic or molecular nitrogen. So then our unit over here would change to N2 molecules. And you can see many other examples in this table here and how the units will change based on what we're looking at, but they all are referenced as a mole.